All right. Now the second problem, you had this 2D heat transfer problem, two-dimensional. So in that two-dimensional, he need to give you the boundary condition everywhere around the plate. Otherwise, you will not be able to solve it, because you remember the computational molecule will end up probably being something like this, right? 1, 1, 1, 1, minus 4. And so every time we write this equation at any point, we will get how many unknown? 5. So the only way to close that set and end up having 50 equation in only 50 unknown is that you need to know the boundary all over it. Right? So those problems cannot be solved if you don't know all the boundary. And we do. So we know all the boundary. And so we are planning to get 9 equation, 9 unknown. That's impossible to solve in a classroom. You need a computer for that. So fortunately for us, he said, hint, take advantage of the symmetry to reduce the number of unknown temperature. So before we even think about the problem, writing the equation and solving them, we have to tell ourselves, cannot be 9 equation and 9 unknown. I bet there are symmetry that will help us to reduce the number of unknown. So where is the symmetry?
1, 3, 7, 9.
Let me ask the question, where is the axis of symmetry? Like, where is the mirror image happening across? This guy, right? This X. Because when you look to the right and to the left, it's exactly the same. So I bet this and this would be the same. Right? So this is not really 3. This is 1. Let's call it 1. All right? And if there's any other symmetry, axis of symmetry? Right. This guy from here to here. If you look to the top and the bottom, they are the same. This axis, there is a mirror there. So if this temperature at point 1 is going to be 50 degrees or whatever, I bet at this point it will be exactly the same. Why it would be any difference? So this and this is also the same. All right? So this point is also 1. 1. Furthermore, right, because of the fact that they are basically vertical and horizontal exactly the same, that make this point 2. 2, 2. So really there is only 3 unknown in this problem. 1, 2, and 5.
We could also assume that 5 is equal to 2 because there's a counterpart of 2.
No, I cannot assume that 5 is equal to 2. Why would you think 5 is equal to 2?
It's T top, T sides, and T bottom plus, or minus 4, T middle equal to 0. So you have to assume that 4 of T2 is equal to T bottom.
I rather write the equation and find out this myself.
Okay.
Because, so it's not for symmetry, it's just right. So let's not assume that 5 is 2 yet. All right. So what does he want from us again? He said determine the temperature using the finite difference method with a mesh size of delta x equal delta y equal to 2. Determine the temperature at the indicated point in the medium. All right. So you guys will start writing the equation for something like this. 2D steady with no heat generation. The equation become this. And writing the finite difference form for it, you open the textbook and you find that partial 2 partial x for any general point m and n would be t of m minus 1 and n minus 2 of t m and n plus t of m plus 1 and n over delta x squared plus t of m and n minus 1 minus 2 t of m and n plus t of m and n plus 1 over delta y squared the whole thing equal to 0. And then you realize that delta x squared is the same as delta y squared, then this equation can simply just become t m minus 1 and n plus t m plus 1 and n plus t n plus 1, sorry, m and n plus 1 plus t m and n minus 1 minus 4t m and n equal to 0. Right? Or computational, or if graphically if you'd like to plot it, it's basically 1, 1, 1 minus 4 equal to 0. So anytime you write this equation, let's write it, for example, here, you will have to combine those guys with u. 1 of this, 1 of this, 1 of this, 1 of this, minus 4 of this equal to 0. So coming to this point, that's worth already 3 points. Alright? If you have this right formula, you get 3 points out of 5. Alright? Now we have to write this formula, and we will write it again 3 times, at 1 and 2 and at 5. Right? Because those are the 5 points that really matters. Sorry, the 3 points that really matter. 1, 2, and 5. So it will end up being T1 equal to 180 plus 180 plus 2T2 over 4, and T2. So why 180 and 180? Because there's 180 to the top, there's 180 to the left. And why there are 2 T2? Because there's T2 to the right, and there's also T2 at the bottom. Right? And T2 become 200 plus T5 plus T21 over 4, and T5 will end up being surrounded like what JC said, 4 T2 over 4. So it just becomes T2. Right? So writing those equations correctly is worth 1.5. So now just solving them together, and solving them together, it's not 3 equations, 3 unknown. Those are actually 2 equations, 2 unknown. So you just solve them by substitution. You take T2 from the first one and you plug it in the first one. You take from the second one and you plug it in the first one, and you get T1 and T2. So T1, which is the same as T3, the same as T7, the same as T9, it ends up being 185, and T2, the same as T4, the same as T5, the same as T6, the same as T8. The whole thing is 190, right? And so getting those numbers right, that's worth 0.5, right? And so this 1.5 for the equation, how do you screw up this? Well, if you didn't take care of the symmetry, you will screw up this equation. So rather than T22, you will end up getting T2 and T4 will show up. You will not lose the whole 0.5. You will probably lose 0.25 of the 0.5 of that equation. So each equation of those 3 is worth 0.5. Right? Question about this?
If you did not use the M and N labels and just wrote out the...
That's fine too. So this equation, Jason is saying you can just write it as T left plus T right plus T top.
Can you write it with just the numbers?
I guess any way that indicate that you have the right formula, it counts. You know, T bottom minus 4 T node equals 0. That worked too. I bet if you can just make this sketch, this cartoon, that's say you got it.
So it's okay if we just write it out with the numbers? You know, just say T1, T2.
So you are saying, what if we start just here? That's what you are saying. What if we start right here and we don't even have this? We don't have any of this. We just start writing the equation.
Yeah.
Well, if you write the equation right, I guess that assumes that you know the formula right. Okay. So that's implied that I know the formula. But if someone, for example, only write this, here is the answer. And worse, they are the wrong number. So he should get the points for the symmetry, right? So that's like maybe 0.5 out of the equation. So what I'm saying is that it really pays to write your steps rather than just assume that I know them, here they are. If you write the steps, that basically helps to document that he know the equation, he know the solution, he just didn't really get the number right.
The symmetry with 2 again.
Okay, sure. So the question Ariana is asking is how can we tell the symmetry? And ouch. I probably can write this again. Okay, so where is the symmetry in this business? So what is symmetry? It's symmetry when you see the right and the left exactly the same. It's like mirror image. You can split this plate by half and you would see that the right will look exactly like the left. Okay, so since those number here on the right, 180 and 200 and 180 is duplicated over here, and this and this are also the same, and this are the same, we can split this plate by half and everything to the right is exactly like everything to the left, right? If you just if we split Jason by half, right ear, left ear, right eye, left eye, half the mouse, right hand, left hand. So we can really think there's a symmetry around him, around his X, right? That's exactly the case in this. Everything to the right is exactly like everything to the left. Okay? If he actually had a pen on his right ear, we cannot split him by half because that breaks his symmetry. Right? So what I'm saying is that if this 180 was 170, we couldn't split this guy and say there is basic symmetry around the y-axis or the vertical axis. All right? Furthermore, there is also, if you look to the top and the bottom in this problem, you can actually think this is also an X of symmetry because everything on top is duplicated exactly at the bottom.
Could you not also say that it's also symmetric between, instead of
The diagonal?
No, the half of the middle.
Let's think about this. So Ariana saying that, wouldn't you think that it's also symmetry around this guy? Well, I cannot tell because those are not exactly those, right? To start with, I don't really know those points. Besides the fact that 150 and 200 are not the same too. But I cannot split here because I don't really know those yet. All right? So symmetry is whenever you can actually see a mirror image across one X. Then you would say, let me solve only half the problem. Actually, if you look at the testing they do in wind tunnels, you will not, actually right now you shouldn't be surprised that in the wind tunnel, so this is the floor of the wind tunnel, and the air is coming like this, you will see what you should see that shouldn't surprise you now after solving this problem. Half the airplane. So they only simulate, there's only half the airplane sitting there with the wing coming up. Right? Because they think, well, why do we simulate we have to test the whole airplane, let's only, but they cannot, for example, do quarter of the airplane, right? So half the airplane because that's their axis of symmetry. So whatever happened on the right part of the airplane will happen on the left part. Right? Yes, James. So, James' question is, would that give us exactly the actual solution around, or the actual flow around the airplane if we cut it by half or not? So this is not a fluid mechanics course. We can ask that question in the fluid mechanics course. But I can tell you that, for example, the separation over here is also, let's have the imaginary part of the airplane. The wake over here will also be duplicated on the wake over there. So there is really a very good symmetry around this airplane that you can work with. All right?